if you are a material scientist working on battery science, for example, there will be some aspects that come to mind when someone is asking you to design a new cathode material or a new electrolyte system. First of all, you would think about what is the material made of? What elements do I want to use? Today we have learned that for sustainability reasons, for example, we would like to move away from something like lithium towards sodium or magnesium, for example. Now, if you have figured out the combination of elements from the periodic table that you would like to utilize, probably the next aspect that you would like to consider is the structure, at least when you're considering a solid-state material, but that might also be true for organic-based systems. So there are a lot of different structure types known in solid-state chemistry. They are tabulated in libraries and you can look them up. Now we try to extend the classical solid-state chemistry structures known by utilizing also molecular building blocks. As a secondary aspect, these hybrid compositions then drastically enhance the space of combinations of elements and molecules that I can utilize to generate materials with different properties. And on top of that, I'm also able to generate framework structures with topologies that are not known in classical solid-state chemistry, simply because I can incorporate molecular building blocks that have, for example, a five-fold symmetry, something that will not be known very widely in classical solid-state motifs. Now, based on this combination, we can generate a modular building block concept if we treat the individual building blocks of molecules and inorganic building blocks as Lego bricks. We can incorporate molecular function in the solid state and add onto that long-range order and some aspects of a band structure. Now, that doesn't have to necessarily lead to electrical conductivity, but it can generate, for example, other kind of band structure motifs that can be relevant for certain applications. And on top of that, most of these materials exhibit internal porosity. Nanoporosity, pores in the size from 0.5 to 3 or 4 nanometer in diameter. But on top of that, my group has early on recognized that those two aspects of designing materials, such as composition and structure, can be drastically enhanced by utilizing aspects of dynamics. So motion in our material, something that we often like to suppress by conducting experiments at very low temperature, or something that is maybe not even considered in solid-state materials, simply because we ignore those aspects of dynamics. But in fact, those dynamic features are critical. For example, in the electrolyte system, when we discuss the motion of ions through our lattice. So the goal of our group is to generate materials away from its equilibrium state. So we want to incorporate some time-dependent changes or mobility in the system by utilizing intrinsic dynamics. And we call these dynamics as something functional that one can tune. So it's not only something that happens as serendipitous, but something where we can tune a material's property towards these dynamic features. And there are two classes of these dynamics that we differentiate, the so-called soft porous crystals. These are materials that show classical phase transitions by expansion or contraction of their crystal lattice, as a stimulation from various aspects such as gas species, mechanical pressure, light irradiation, electrical stimulation, or changes in temperature. And secondly, we can also consider robust dynamics. So in this case, our lattice, our crystal lattice itself is rigid. It doesn't deform. There's no change in volume. However, we have some mobile groups on the interior of our pore space in the material that change their structure as a function of time. So something dynamic. And I will show you some examples of what we currently work on. So this was one of the earliest materials that I worked on during my PhD a few years ago. And here you can see the effects of these volumetric contractions in a dynamic, flexible metal organic framework. Now in this case, the volume of this material is contracted by about 50%. So it's a huge change not only in the macroscopic aspects of this material, but also in the porosity that you can see here indicated as these colored spheres. So we practically compress the whole mesoporosity in the system. This is a purely elastical process. There's no chemical bond broken or recreated in this process. It's simply like squeezing a sponge and back expanding it again. Now, another aspect that we currently work on is the incorporation of so-called molecular machines, in this case molecular motors. Now here you can see the molecular structure of such a motor. It has a double bond in the central part here. I will replay this video. And if we irradiate these molecules with light, they start to rotate unidirectionality. Yeah. And so we have identified with computational methodologies that actually by incorporating such rotating species in a pore channel and controlling their directionality, we can pump a fluid, not only accelerate the transport, so activate the transport via the translation of this rotational momentum, but we can even direct the transport, meaning that if your rotor rotates clockwise, it will push the fluid in one direction. If it rotates counterclockwise, it will push it in the other direction. And this is something that you can see here. So in a lot of different cases, this is not the case, but here you can really see the change in directionality. Now, in a lot of molecular framework materials, such dynamics are actually already present. And often we don't really consider them because we try to build the materials as rigid entities. We want to have them stable, so we ignore these dynamic features. Now, over the past years, we have built some expertise by utilizing low frequency or terahertz Raman spectroscopy. So it's this section of the Raman spectrum that you can see here that is usually cut off in your regular Raman spectrometer or in your microscopes. Our setups have special filters that give us access to this region. And in these low frequency regions, we observe lattice modes. So these are phonons. In this case, it's the dihedral twisting of these phenyl groups within the crystal lattice. And that is something that happens and can be activated, for example, by changes in temperature. And so you can already see from this animation that this kind of racking motion of these ligands has a very strong effect on the change in the pore window size. Yeah, so if you are looking for a system that can actively change the transport properties, you will have such a dynamic pore window. It can sort of not only facilitate the change in accessibility to the interior, but potentially, if we can drive it with an energetic input, also activate the transport properties. So quite recently, we have utilized these systems to also look into ion conductors of solid electrolyte systems. This is in collaboration with Bettina Lodge from the Max Planck Institute in Stuttgart, where my research group is partly located still. And we looked at this sort of lithium ionic conductors based on a series of solid solutions in which we vary the ratio between silica and tin. You can see that there's no real clear correlation, but on top of that, we were able to find some Raman features that are sort of responsible for these changes in the ionic conductivity, which is something that brings me to a topic that we are currently reading into, which is the aspect of plastic crystals. So some of you that work on solid electrolyte systems might be familiar with this kind of field. Usually these kind of materials here are shown as a very crystalline structure, but in fact if you record these materials at ambient temperature, you probe them with powder X-ray diffraction, you will recognize that they show amorphous features. We have seen at several talks today actually that upon charging, discharging, some cathode or even electrolyte systems lose long-range order. So that comes in again with not only losing the long-range order but also complete changes in the mechanical properties. For example, the mechanical rigidity is strongly reduced when the crystal lattice is losing this long-range order. And these kind of systems, this recent work shows that strongly anharmonic phonon-derived vibrations of the crystalline lattice and stochastic hopping dynamics of the mobile lithium ions drive this high ionic conductivity. So we have the combination of a deformation of the building blocks in the crystal lattice in addition to the hopping of the lithium ions within the interspatial parts of this crystal lattice. And so here you can see some MD simulations that the authors have looked into where you can really follow the hopping of these lithium ions in this kind of lattice, both treating this lattice as a fixed lattice and also treating it as somewhere where the intrinsic parts of the system are dynamic. So the fundamental question for us that we would like to address within the consortium of POLIS is, can we utilize intrinsic dynamics of these molecular framework materials to accelerate the transport properties of challenging multivalent ions? And we have selected magnesium as a challenging ion where we are still looking for solid electrolyte or in general electrolyte systems with high ionic conductivity. And these are two MOF material systems that we currently look into. So you can see these pore apparatus here, which upon exposure to solvents, for example, but also other liquid systems, can expand and contract. So we have a system that can responsively adapt to the interior of the pores. in this case built on a heterocoordinative system, both featuring a pyridine and carboxylate-based system. While in addition to that, we are also choosing systems that have more discrete trimeric clusters. This gives the system more flexibility in all 3 dimensions of the crystal lattice, which is something that is pretty critical for the electrolyte system, because we cannot control the directionality in which the crystals are immobilized. And so in this case, in worst case, your ionic transport will happen perpendicular to the pore channel. So we have a 1-dimensional porous system versus a 3-dimensional porous system, both featuring responsive or dynamic building blocks. But we want to push the MOF chemistry a little bit further and try to also utilize it not only as a dynamic platform to transport the magnesium ions, but in addition to that, we would also like to utilize the chemistry of how these materials are made to improve the interaction between the electrolyte system and the electrode. In this case, we want to use an approach called mesoscopic replication. This has been demonstrated with several different metal oxide species. So in essence, you take a metal oxide precursor, you bring it in contact to the organic ligands under certain reaction conditions, can be different pH values or different solvents, different temperatures, or even application of an electrochemical stimulus. And we can structurally recreate in this case an inverse opal structure into a MOF-coated structure. So you can see that most of the inverse opal is gone, and it was directly spatially recreated by the MOF crystals. So in this case, this would allow us to directly grow an electrolyte system onto a metal electrode and incorporate much better contact between the electrolyte and the electrode. And in addition to that, utilize the reactivity of the metal oxides to directly get rid of the passivating layer that you don't want to have on the electrode in the first place. So we hit 2 birds with 1 stone. I guess that's the English saying. So the benefits from this is that we would like to use the dynamics for high ionic mobility for challenging multivalent ion system, and that's something I forgot to mention. So we will utilize the approach of a semi-solid electrolyte system by incorporating ionic liquids into the porous system as a sort of secondary ion mediator, right? So there's a lot of research that has already been done in Jürgen Jannik's group or Timo Jakob's group in Ulm on these kind of systems. So it will not only be the bare porous systems, because obviously the magnesium ions will not hop in vacuum through the system. We will suppress the electrode passivation by on-electron growth of these MOFs, explore the role of dynamics in electrode-electrolyte interfaces towards self-healing properties, and explore the concepts of polar ionen by surface modification of the framework material. So for example, grafting different functional groups on the interior of the pores and probe what their effect is on the transport mobility and the effective charge on the ions. Some added value that our group brings into the consortium is we have a lot of expertise on terahertz low-frequency Raman spectroscopy, both as a spectroscopic tool but also with confocal microscopy. And Mikael Lindén also has experimental setup for this. And we also have a lot of expertise in gas adsorption analysis of porous systems in general. So if you have any questions about characterization or analysis in that regard, we are happy to help out. And in addition to that, we also have vast experience in the synthesis and specifically also the activation of molecular framework materials like MOFs and COFs. So with this, I'm thankful that I can be here today. I thank you very much for your attention. I'm happy to answer any questions.